Hi everyone, and thank you for joining us in yet another exciting Munich NLP event. For those of you who are joining us for the first time, we are a group of NLP enthusiasts based in Munich, coming from both industry and academy, and our main focus is organizing events like this one in which people can learn something new, hopefully, about NLP and discuss ideas. Today, we have the pleasure to have here with us Niels Fleischmann, who works as research engineer at Pruna AI, a German-French startup with the mission to make AI models faster, cheaper, smaller, and greener. In that regard, he will be telling us about different compression techniques to optimize model performance during inference. And if during the talk you have any questions, please write them in the chat, and we'll get them answered at the end of the talk. So with that, I pass it now to Niels. And Niels, the stage is yours.
Thanks for the nice introduction. And hi everyone, I'm Niels. I work as a research engineer at Pruna AI. And I'm actually super happy to be talking here today because I watched the videos of Munich NLP for a long time. I think it started all when ChatGPT 4 came out. Back then I was studying data science, had no clue about NLP and was just curious. And I think your channel was the first thing I found. So I kind of binge watched all the videos. And it has been 2 years. Oh, huh? Is it? Ah, has been 2 years since then, and a lot of things happened, as you also might know, in the space of NLP since then. And to show you this, I brought this amazing chart by artificial analysis that shows the output speed measured by tokens per second against the intelligence index, which is kind of an average over different benchmarks. And on the bottom left quadrant, we see a good old GPT-4. Over the years, they improved their model. So the first thing they did was they released this ChatGPT 4 Turbo model, which was a bit faster, a bit more intelligent even. And then afterwards, they kind of switched to the 4.0 version, the Omni version that had even new capabilities, was way faster and also more intelligent. And even within this 04 product, this 4.0 product, there had been some improvements over the last year. So, like that point here we saw was May last year. And since then, it only got faster and even more intelligent with the last March update. Which is, I think, quite amazing that over the span of only 2 years, this model kind of got like, what, I don't know, 10x faster, more intelligent, and even cheaper. If you look at this chart here, also by artificial analysis. So, the question I ask myself then is, I mean, what made this all possible? I mean, how did these models get efficient over the last 2 years? And in this talk, I want to provide you with some answers. I want to present some of the approaches to make models more efficient. And I think like what made this possible are two things. So for one, of course, there is a lot of improvement also happening on the side of these research labs that made these models. So there is some algorithmic improvements. If you, for example, think of mixed of experts, for example, or also now this new post-training with reinforcement learning, and also like on a data regime, there is like improvement. So this is one side, but that's not really the side where we can do much about it, right? We just get the models. But I think the more interesting side for you, maybe as an end user of these LLMs, or maybe as a tinkerer that plays around with them, is inference optimization. So taking these models and then try to make them as fast as possible. There are different approaches to do that. So, for example, some companies like Cerebras, they work on specialized hardware that make running inference with models faster, whereas we as Pruna, we focus more on algorithmic tricks and techniques to, in the end, speed up inference of these LLMs. And to begin, let's start with some basics, and let's talk about tokens first. Here I brought you the announcement text for today's meetup. Yeah, here scaling has fueled the latest breakthroughs and so and so. Right? We as humans, we can read that and immediately understand what it means, but how do like large language models do that? Usually they use some sort of tokenizer, which will then split this raw text into these word, subword chunks, these so-called tokens, which it represents basically just as some index, right? And each of these tokens is then represented as a vector by these LLMs. So actually, vectors are how LLMs think about these components of text. So for example, if you take the beginning of the announcement, this scaling, which is split up into like two tokens, sk and ailing, right? You have maybe some big lookup table where you can basically take this index of this respective token and then get the respective vector that kind of represents the gist of what this token means. Mm, which is, by the way, all learned during training. And the same here, of course, for ailing. Nice. Then also a quick recap. How do these LLMs even work? So let's say we have like this input text. We start with scaling, right? Which we, as we know right now, we split it into like these two tokens, get these embedding vectors, and then what we usually do is we feed in the sequence of these vectors into a neural network. And over the last 3 years, very consistently, this network has been a transformer. We will maybe later talk about some insights about this, but in the end, what's important is it's a really large large network basically, which outputs a probability distribution over these tokens. So basically, given like some input sequence of several tokens, it then produces a distribution where it assigns basically every token there is a probability between 1 and 0 of how likely this token will come next. And so far, we just assumed that we have these tokens to begin with, but of course, this is a decision, and it's also always a trade-off, right? So one important decision is how many tokens do we even have, right? How big is our vocabulary? And basically, the trade-off here is if we, for example, use a small vocabulary, so we use few tokens, then we would need more tokens to present the same amount of text. So in this case, we're very inefficient, whereas like for a larger vocabulary, we can like represent text with fewer tokens. But the flip side of it is kind of, as I said, like we have this prediction at the end of the large language model. And if we have too many tokens, like this prediction problem of predicting the next token gets more and more complex, especially since we also then will have like very rare tokens. And here on the bottom, we kind of see how this looks like. Here I have like the tokenizer used for GPT-2, which had like, I think, 500 tokens in its vocabulary. And I think it had really problems with like, for example, coding text. So it really tokenizes this text inefficiently. Whereas like this CL100K, which has like 100,000 tokens in its vocabulary, can represent, for example, this text and overall more texts more efficiently. So it's probably closer to like the sweet spot in this trade-off here. And also, one interesting aspect, I guess, is like, okay, now that we have fixed like the amount of tokens we have, like the vocabulary size, still the question remains like, what should be the tokens that we use for our model? And here, what usually modern tokenizers do is they kind of look at like this data that is also used to train the models, and then kind of see, okay, which syllables, which words appear very often in it, and then like these very frequent words, for example, become their own tokens. And since most of the corporas that are used are mostly English, these tokenizers are really efficient in representing English language. Whereas, for example, if I would have like translated this announcement text to Bavarian, the tokenizers would be very not really efficient in representing this text with few tokens. So it wouldn't like need more than double the times of tokens compared to the English text. And one idea, and that's something we have already, but some idea we have at Pruna right now is to maybe find a way to kind of post-training change the tokenizer to maybe adapt it to the domain the language model will be used in. Um, okay, let's maybe go back and for the next way of improving models, go back to how large language models learn. And it's also something you might know already. So LLMs learn by predicting the next token. So usually you have like these large amounts of text, maybe scraped from the internet. And so what you do is maybe you feed in like the start of some text sequence you have into your network. So for example, that could be scaling as in my example. Then you produce like this output distribution with your transformer, and then you kind of already know how the sequence continues, what the next token will be. So what you can kind of do is you can basically see, okay, what probability did I assign to the actual token that comes next, and then and I don't go into the details here, but then you can kind of slightly adjust your transformer so that the next time you kind of see like maybe this beginning of a sequence, you will assign to the actual token that follows it a higher probability the next time you see it. And basically you use this really sparse target. So that's one way of doing it. But over the past years, another very popular way of training networks emerged, which is like distillation. So oftentimes, like these big research labs have these really big models that they train for a long time, right? That there's much that goes into it, like for example, all of these post-training steps, so that the model really gives you the nice outputs you want from it. And then the idea of distillation is kind of using this big, usually big model to create some training data that you can use to train a smaller model. So, for example, you could also feed in like this big teacher model, some sequences, like for example, here again, like this beginning of my text, like with beginning with scaling, right? And that it produce some output distribution. And then what you can do is you can use two outputs of it. So either you can go ahead and actually work or like save these soft outputs, which kind of convey a bit more information because it's not like really one hot encoded. In this case, for example, I think is and has are possible tokens to follow up on scaling. So it kind of has all of this notion that this teacher model has learned in it, and or you can also just take like the output of this model and then use it basically to train a much smaller student model, which will also be a transformer usually. Um, which of course also produces some output distribution, and then you can kind of either use like these hard targets of the teacher model, or you can use even the soft targets to train the student model. And apparently this works much better than just training the smaller model from scratch. So that's why everyone is doing it. There also has been some other improvement in this regard. For example, if you think of the Phi series that Microsoft does, so here the idea is interesting. So the basic idea is to let the teacher write a textbook for its student, kind of. If you think of it, right, the internet is full of text that is not always high quality. So not all text on the internet is like Wikipedia-like quality. Much of it is messy. So the idea here is maybe if we have like a really knowledgeable teacher model, we can use it to kind of write textbook-like data, a text that really explains concepts well, from which like the student can learn faster, and it actually seems to work. I mean, one other aspect one benefit of using such a teacher to generate synthetic data is that you can really control like the data mix that goes on into your training corpus that you use to train the model, which is really important right now. And in particular, like using such a teacher model is really important for this reasoning data because that's some data that you don't find usually on the web, right? I mean, there's no blog where someone just like dumps his stream of consciousness, his reasoning trace in this blog. So you don't really find this detailed reasoning steps on the internet. So that's where it really helps you if you have like already trained a teacher model that you can then use to kind of generate this type of synthetic data from which a smaller model can learn. And here I have brought you another chart from artificial analysis that kind of shows you um, how well it actually works. So in dark blue on the top left, we have the DeepSeek R1 model that's obviously very smart, but also slow. And here the next point we see it is like a distilled version of it. It's like a 14 billion parameter version of it, which is like really insane because I think the base model is like 700 something billion parameters, so really big, and like you can really distill it into like a really small model, which still is pretty smart, right? So for example, if you compare it to the Llama series of models, which you see here in a lighter blue, right? You can also do distillation for them. I think Meta already does that for you. But you can kind of see that this distilled version of DeepSeek really hits a sweet spot because it's with 14 billion parameters much smaller than, for example, the Llama 400 billion parameter model, but still more intelligent and faster. And I think you already have seen that with like the O3 mini model, which was much smarter than like the O1 model while being cheaper and faster. So I really think like that distilled versions of models are a super good compromise between speed and quality. And actually, um, because it works so well, to me it feels at least like OpenAI is a bit scared of it, right? So one reason why, although you pay for all of these reasoning tokens, you don't see them, right? For these O models, is that maybe OpenAI is scared that competitors can maybe use these reasoning traces to train and teach their own models, and distill basically O freeze, for example, capabilities into their models. And there have also been some accusations from the side of OpenAI because they kind of said, oh, this amazing DeepSeek model, they probably distilled their model from OpenAI's models. So yeah, it's a really powerful thing that can really produce smaller but also faster and still capable models. Let's go a bit back and focus on a different aspect. Let me now talk about a problem that NLP had for a long time until like this rise of these big LLMs, which was that language in itself is super complex and oftentimes context dependent, right? Here I have brought you an example, for example, swing the bat. And here, of course, if we read this, we already immediately know that bat in this case refers to something like, for example, a baseball bat. But in different contexts, the same token can mean different things. So, for example, in this example here, in the cave, I saw a bat. Obviously, bat doesn't refer to like a baseball bat, but to an animal. Um, and that's a problem because, as I said, right, we kind of use the same vector to represent each token. So just by this vector, we don't really can tell the difference between these two types of bats. And that's why basically this transformer paper that came out almost now 10 years ago with its attention really was a game changer back at the time because, and now I will also stay on a high level. The idea here is that maybe we don't really can know what bad means by just looking at itself, but if we can maybe use the context or like the tokens that come before like this token, we can kind of infer the meaning of this token from the context. And that's basically the rough idea of this attention mechanism that is used within the transformers. Yeah, which is basically, let's basically use the previous tokens to kind of update and enrich this token representation for this token bet in this case. And here, for example, the tokens z and ing that make up the word swing, they kind of give it away, right? Yeah. And why did I tell you this? Because actually, the way that attention is computed, if you like just code it up naively, is very inefficient, and I will quickly show you why. So here we have like an example video. I will turn down the speed a bit. And we have an example video of, for example, a generation also with an LLM looks like. So at the beginning, we start with a beginning of sentence token that we use to kind of tell the LLM that like generation starts from there on. And let's see how this generation looks like. And especially like this attention mechanism looks like. So we start here with the beginning of sentence token. It only pays attention to itself to enrich its representation to then kind of predict the next token, hello. And you will quickly see that, as I said, if we do it naively, we kind of would redo like this attention for this beginning of sentence token, which we already like did in the first for the to generate the first token. Then we would do like the attention for the token hello, and then the next token would be world. And I hope you can see it. We always redo here these attentions for these previous tokens that we kind of already knew, right? Um, and in this way, this attention mechanism or this causal attention mechanism that we have in these autoregressive LLMs is by itself a bit inefficient, but fortunately, there is a really quick and easy fix for that, which is it's called KV caching. And the idea is just, right, instead of like recomputing these attention, these expensive attention operations that we already know, just store them in some cache. And that looks, for example, like this. I will also make it a bit slower that you can see how it goes, right? So here in this case, here we would, for example, compute this attention for this beginning of sentence token, and then marked in blue, we would save it in our cache. Same for hello, we compute the attention for this hello once and then save it. And that means for the next token, we don't really have to redo this computation, which saves us a lot of compute. This is the rough idea behind KV caching, which is, I think, also pretty much implemented in many libraries. There's still, although it feels like it's like just a free lunch, there's still a trade-off, of course, because it takes some memory to store all of these outputs. So yeah, the trade-off here is kind of okay. We need some memory to store all of these KV computations that make up like the attention, but the big benefit is that it makes everything much faster because we save a lot of computations in this attention, and of course it really is dependent on like which GPU you use, which model you use. But I think I saw some numbers where they said like it makes generation roughly 5x faster in some cases, especially of course for long texts where like this repeating all of these computations is really tedious and costs a lot of compute. Yeah, so it's something you usually want to do. And before we dive into some other ways to make your LLM faster, I will try to quickly explain you on a high level how GPUs work and how we can maybe make computations faster on them. And for that, I will use this metaphor of a GPU as a warehouse with its factory. I will quickly explain this metaphor. So maybe let's go through like the specs of a typical GPU one by one and kind of explain what it represents in our metaphor. So here I took the specs of the GPU I'm using. I'm using a L40S on my working machine, and the most important spec there is arguably like the GPU memory. Probably something you also know about your GPU. In my case, it's 48 gigabytes. And in this metaphor, you can think of the GPU memory as the size of your warehouse, right? And so, for example, what happens when you, for example, have a code and like you move your model to your CUDA device, then what will happen is basically you will just shift all of the weights and biases that make up your model to this warehouse, right? But by itself, moving it to the GPU doesn't do anything, right? It's just you just brought all of these numbers to your GPU, but in the end, really the magic of these numbers happens when you do some linear algebra with them, when you do like these attention and linear layer computations with them. And for that, you kind of have to bring these numbers, these weights, these biases to your factory, which is like the GPU cores that do all of the computation. And for that, probably one of the most important numbers is the memory bandwidth. That kind of describes how fast you can move your weights and biases that make up your model from your warehouse to the factory, the GPU cores. And in my case, it's something 800 gigabytes per second, so quite fast, but yeah. And then so far, I think I depicted in this metaphor like the factory at the same size as like the warehouse. But I think it's actually better to imagine this factory as being super small. So for example, the L2 caches, the lower level caches of your GPU, they only have space for 48 megabytes, not gigabytes. So it's and everything that has to go to the GPU cores has to go through this like cache. So you can kind of imagine we can't just say, okay, let's bring all of the whole model to your GPU cores and then do some computations with it. You rather have to really shift like parts of your model one by one to your compute cores, do some computations with them, move the result back, and so forth, right? Um, and maybe like the most interesting number when thinking about your factory, your GPU cores, is the number of flops, which on modern GPUs really depends on the data type you're on. Usually you use something like bfloat 16 or float 16 for LLMs. And then here for my machine, I have like 360 teraflops, also operations per second, which is like also insane. Yeah. Okay. Now that we kind of understand this metaphor, we can think about, okay, what could be like some problems with our factory? Why can't we like what could be some bottlenecks of this factory of our GPU? Why can't it be faster? And I think the most intuitive reason why you could think that maybe we're not as fast as we maybe could be is because we're compute bound, right? Maybe the problem is that our factory is just not fast enough at making all of these computations. And for training LLMs, which is very compute intensive because you also have like to compute the backward pass, you're usually compute bound. Usually like the amount of operations you can do per second is really like what limits you and your GPU. However, for inference, and we're interested in inference, the memory bandwidth is usually more important. So actually, in most scenarios where we do inference with LLMs, we're not limited by the fact that our GPU cores are not fast enough, but rather that we can't really supply our GPU cores fast enough with new ways to do some computations with. And so let's kind of think about how we can tackle this memory bound problem. And for that, maybe let's look at this very simple example. So let's say we want to perform this computation you see here on the right here, right? We want to have some input X, right? We want to do a linear operation on this input and then followed up by some norm to obtain an output Y. If I would have coded up this code, like probably pretty simple code in PyTorch and run it on my GPU, what would happen is the following, because usually by default your GPU will just operate the operations sequentially, and it would like look like somewhat like this. So at the beginning, I have to take my input X and my linear layer, bring it to my GPU, then do this intermediate computation, get an intermediate result Z, bring it back to my warehouse, to my GPU memory, and then again take it and bring it with like the parameters that make up my norm layer to the GPU again, then do this norm computation until I finally have my output Y. And as you might think, right, as I said, if like our memory bandwidth is a problem, it feels a bit like wasteful to kind of move things around that often between our warehouse and the factory. So what we kind of want to do is maybe we can just bring the norm and the linear layer and the input to the GPU at once, do the whole computation there, and then just bring the result back. And in fact, that's something you can do if you have a custom kernel for that. And kernel, I know it's like a super overused word in machine learning, but in this context, it means GPU kernel, and it's kind of like custom code that tells your GPU how to do some operations. And if you have written some kernel, for example, how to perform like this operation consisting of a linear layer followed up by a norm layer, what this allows you to do is kind of to what I described, right? You kind of can move all of these things all together from your warehouse to your GPU, do the whole computation there, and then you're done, right? And this is where you don't have to move things around that often, and you kind of save some of your bandwidth, which really helps you to be faster. Um, the good news is because I can tell you writing CUDA kernels is no fun, and you don't really have to do it because there are many cool tools that already do it for you. So I'm pretty sure most of you have already used this, and it's called operation fusing, what I showed you. And I think most of you already used it because, for example, Torch Compile does it. I mean, to me, always I just accepted Torch Compile made things faster, right? You can just pass any NN module to Torch Compile, and then it somehow is faster, but actually what happens under the hood, as depicted also here, you kind of have maybe some code written, and then what Torch Compile will do is it will construct a compute graph that really shows in detail which operations are performed for your operations, for your code. And then what it will do, Torch Compile, is it will look for every maybe for operations that are followed by each other, it will look, oh, do I have already a custom kernel for these operations and can I maybe fuse them together to make it faster? And to me, that's really magical that this works. And yeah, and I think you all already experienced that it works because it makes really things faster by fusing operations together. One other thing where fusing was used, and I think which was big news in the NLP community, was flash attention. Um, and basically, what flash attention did, uh, I recently talked about like this attention mechanism, and basically, what you also want to do to make this attention mechanism faster is to fuse together the operations that make up this attention mechanism. And the problem, so like for a long time, was always that there was this the softmax operation as part of this attention layer. And so somehow people did not manage to kind of fuse that with the other operations. So we first have to do like all the computations before the softmax, and then it was basically a lot of shifting things from your memory, from your warehouse to your factory, back and forth, which is not ideal. And then some people found out how to do it more in a more clever way, where you can basically fuse like the operations you do before the softmax with the softmax, and even operations following the softmax operations, so you can kind of fuse together more operations, and this way this made all things faster. Good thing again is you don't really have to do it yourself. I think if you use, for example, Hugging Face transformers, it will already do that for you. It will already like use flash attention for you. And I think here we have some nice numbers to really see the impact of this. This shows you kind of the speed up you get for this attention computation, which really is like an expensive operation in your transformer. And as you can see here, in I think blue, it was is without like flash attention, and as you can see with flash attention one, in orange you can I think improve like the speed up, like speed up the operation by 2.5x. And then these people continued, right, and then they developed flash attention 2 and 3, which also I think make use of some specific capabilities of modern GPUs to make things even more faster. Um, But let's come back at the problem. So operation fusing, torch compile, flash attention, these are all ways to make it faster, but we can maybe also try to like invent or like do different things to make things faster. So the key thing here to understand is that usually the model weights are like our biggest problem, because yeah, these big weight matrices, they are really like what causes these models to be like these many gigabytes large. So actually, like for example, the inputs or like the activations, these weights of these layers in our transformer, they consume most of our bandwidth. So one thing we can do if we are interested, for example, in increasing our throughput, is just to batch basically multiple generations together. Because I mean, we have to move this huge, bulky linear layer to the GPU anyway. So why not just like then also pass, for example, four inputs as well to the GPU? And as I said, like right, this computation of like four different inputs is not really the problem, because like our GPU compute is not a problem, right? It's just the bandwidth, and for this reason, batching can make sense to increase the throughput. That's one thing we can do. But one other way or one other idea is, maybe if these weights are like the big problem we have, can we make them somehow smaller? Can we shrink them? And turns out we can. So first of all, again, think of these linear weights as like it's these weight matrices. Basically, it's a bunch of numbers, usually floating point numbers, and yeah. So how can we basically shrink them? What can we do? And here we can do what's called quantization. So here in this graph, you see in the top the because like the numbers, as I said, like by default are usually represented via like 16 bits floats, like floating point numbers. So you can cover a wide range of numbers with these FP16 representation. But the idea of quantization is, okay, maybe can we also like represent the same numbers with less bits, for example, with only like 8 distinct values. And yeah, that's the idea of quantization. So basically, you project like all of these values that are in this float range, all of these weights, you project them down to like maybe, for example, only 8 distinct values. Um, and this way, you lose some precision in the way you represent your numbers, which can also, of course, introduce some errors, but it makes everything much smaller. So, for example, if you use, for example, int4 instead of like BF16, you make your whole model 4x smaller, which kind of also means that you can shift it around and shift its linear weights, for example, around much faster between like your warehouse and your factory. And yeah, the reason actually it's an one would think that like doing this would completely destroy the model, but for example, going down to 4 or even 8 bits, usually that's not really that big of a problem, because yeah, the differences are still rather minor, or like in the last points after the decimal point, right? And for example, here's like a really recent paper that's called Yet Another Quantization Algorithm. It's, I think, right now pretty much the state of the art. And what you can kind of see here, they have some results for the new Gemma model. And in the top row, you kind of see the results for the normal unquantized model that uses 16-bit for each of its weights. And here you can kind of see like the different benchmarks of this model. And here you see kind of the results of this quantized model, which only uses 4 bits to represent all of the weights. And actually, surprisingly to me, although this model is 4 times smaller, the metric results almost seem similar, right? You sometimes lose a few percentages, but not even. I think there are even like some benchmarks where you improve for some reason, which is really interesting. So um, this is one thing we can do. Okay. Now let's also talk about a different aspect in which we can maybe make our LLM faster. Because I think if you look at like LLMs and what they do is one thing that to me always felt a bit inefficient is that for each token you kind of use the same huge bulky transformer. So you kind of spend the same amount of compute for each token. And if you look at language, not every token is equally difficult to predict, right? So for example, here I have this example. Maybe let's say I ask an LLM what is the square root of 7, right? And then the LLM answers me, the square root of 7 is 2.646. By the way, I didn't check it. I hope it just is right. But I would assume like most modern NLP, large language models would be able to like get the right result, right? But if you really consider like this answer of this LLM, the first part of it is just like rephrasing my question. So I would assume it's pretty easy to come up with these tokens because it's just like reusing what I already asked it. Whereas like the end of it, right? For example, I wouldn't be able to like tell you the square root of 7. So it's really impressive that they can do it. And I would assume that's also really hard and it's something that where you really like need this really bulky transformer to come up with the right result here. But still, right? Most of the tokens are quite easy. So it feels a bit wasteful to use like a big LLM for that. So let's assume the following scenario. Mm, Assume we have a super smart, super big, let's call it target model, right? It's a super large transformer that knows a lot of things, right? And maybe we have like a more stupid version of it. Maybe a distilled version, for example, and let's call it a draft model, which is of course smaller and also faster. Using these two LLMs together, what we kind of want to do is, right? Ideally, we want to use like this the stupid model for all of the easy tokens, and then we use like the smart model um, for all of the difficult tokens here, right? That's what we want to do. But I mean, the problem is, how can we kind of tell or know which token will be easy and which won't? So one way of doing it is the following way. So let's maybe take our stupid model and let it produce some draft. So let the stupid model answer and produce an answer. So in this case, maybe the stupid model will say something like the square root of 7 is, and so far it's right, but then we'll come up with something that doesn't make sense, 47, for example, 49, for example. And so let's say we have that, and then maybe we can do the following. Maybe we can then use our target model or super smart target model to kind of check this draft that our stupid model produced. So here in this case, it would say, oh yeah, the first part looks really good, all fine to me. And then here it would kind of say, okay, maybe that doesn't also make sense to me, so maybe that's wrong. And then maybe it will correct like this token that was wrong, and then the draft model can continue from there on and try to like produce a new draft that continues from there on, maybe something like this. Still wrong, but maybe at least it got a point here right. So yeah, I think you get the idea, right? How you can maybe do that. Um, and I can also show you an image, maybe also gives you some intuition on how that looks like. Um, uh, and by the way, a video by Google, which also I think Google DeepMind came up with this idea of speculative decoding, which all of this is called. And here you kind of can see in action. So on the top, you have basically just like this huge bulky target model working itself through like the answer token by token. And on the bottom, you have speculative decoding where you have this stupid model and this smart target model working kind of together. And we'll just play it. You can see like this draft model will produce like long chunks of text really fast. And then like the target model will look at it and then see how far like the answer seems correct and then um, accept or reject like parts of this draft. And see this direct comparison. This way, you are faster in the end. Okay. I'm not sure if you should wait until like this target model alone is done, but yeah, let's continue. Um, Okay, maybe one thing. So far I just said, yeah, we can use this target model to accept or reject like tokens. Seems a bit, yeah, how? And so how it's done is the following way, right? Basically, both the stupid and the smart model, they're both LLMs, so they will both output a probability distribution over all tokens, right? And so, for example, here, like the input sequence looks like this, and then they both are able to produce like this output distribution, and maybe they kind of assign like different probabilities to like the token that was in the end chosen by the draft model. And so the rule one, which the target model uses to like judge if it will accept or reject a token, is if it assigns a higher probability to the selected target draft token than like the draft model, it would always accept this token. And in case like maybe the draft model assigns a higher probability to the token it outputs compared to like this target model, in this case you would accept this token with a probability of like the probability of like this target model for this token divided by the probability of like the draft model of this token. And turns out, and here you just have to trust me because I don't want to go into details, but trust me, I studied math. This works out, and in the end, if you do this like this, if you sample like this, you get actually the same output distribution as you would have gotten with the target model alone. So basically, like this team of stupid draft model and target model is producing the same kind of output as the target model, which is to me really magical and really nice. And maybe something I did not really explain that well right now, and something you can might ask yourself is, right now I say kind of to accept or reject like this target model has to also compute this like do like this full pass through the transformer, which kind of means to kind of end up with this output distribution, right? So, I mean, how are we speeding up things? I mean, couldn't we just then, if we do like this, couldn't we just like use this target middle model in the first place? And it's a really valid question. And so the question is, where does the speed up really come from? And so far, I kind of presented it in a way where kind of the target model sequentially goes over the draft and then token by token accepts or rejects, right? But what you can do, because like the draft will be finished, right? You can kind of process like all of this in parallel, right? You can in parallel kind of assess for each of the generated tokens, do I want to accept or reject it? And that's kind of where the speed up comes from, because, and that's also something I explained previously, right? Batching together multiple generations is something that gives you a speed up because you are so bandwidth bound, right? Um, and here you also have some numbers, I think, from the original paper, which was like 2 years ago for like Google's T5 model. And of course, it really depends on like which combination of target and a draft model you use. But for a good mix, you can sometimes really achieve a speed up of around 3x, I think. And it's actually something that you might already have benefited from because Google, I think, rolled it out for their smart answers to prompts on Google. So I think you already have seen this. And on the left-hand side, you can see how it looked like before they used speculative decoding. And on the right-hand side, you see how fast they are like with speculative decoding. And yeah, let's wait a bit. Okay, here with speculative decoding, we already have an answer here, and it takes much longer without it. So quite cool, I think. Yeah. Okay, I think we went through a couple of optimization techniques. So at this point, I also want to explain a bit what we do at Pruna or who we are and what problem we will try to solve. And I recently came across this talk from Björn Ommers, who's a professor at the LMU. And I think this slide he had for his Republica talk was really nice in summarizing what we try to solve, right? So, and that's also something you know, right? The chart on the left, the models got bigger over the last years. And here you kind of see like the model compute from the models increased by 4x each year, which is really insane if you kind of pay close attention and see that like this y scale is like a logarithmic scale. So these models over the past years really heavily increased their demand for compute. Whereas, of course, like graphic cards, GPUs also got better, but at a fast, um, way slower pace. So there's kind of this imbalance between demand in compute and supply by these individual GPUs, that I guess will only keep increasing over the next years, right? And so one obvious solution, so for example, if like the single GPU doesn't like really grow at the same rate as like these models demanded, one way is just okay, we need more GPUs, right? And that's what you already see right now with, for example, OpenAI and their Stargate project, right? They right now spend $500 billion in building these huge energy consuming data centers to power the next generation of AI, which to me in times of climate crisis and so on always felt a bit wrong that we kind of spend now so much compute on these models, right? So what we in Pruna believe in is a different solution to this problem of this increasing demand, which is machine learning efficiency research. And here I brought you a nice graph from the Hahn Lab, the MIT Hahn Lab, that kind of showed how the number of publications in one very relative subfield of efficient ML kind of increased over the past years. Pruning, which also I can think gave Pruna its name. And what you can see here is that also the research in making this huge model more efficient really increased over the last years. So there are many cool ideas on how you can kind of take these big models and make them smaller. And kind of as Puna, we see that and we want to help because I think one problem there is with these research ideas, right? There are like a lot of cool ideas, but usually how research goes, right? You publish a paper. Nowadays, oftentimes you even publish some code, but this code is usually not really like product ready, right? So it's oftentimes really hard to use the code that these researchers used. And we as Pruna try to build this gap, basically, this bridge between like research and production, and take these ideas from research and make them very easy to use for you to kind of speed up your inference. So we recently published. Our open source repository has an Apache 2.0 license, where basically what we do is we make it really easy to use different algorithms. For LLMs right now, I think we have really good quantization algorithms that also combine well with different compilation algorithms. But of course, we are continuously working on adding a new algorithm and new algorithm combinations because, and I think that's also maybe some key thing that you can take away from this talk is that we believe that by combining different approaches, you can in the end get the best result in speeding up inference. So I guess if you like what we do, check out our GitHub repository. I think we also have endpoints on Replicate where you can just use the model without like running it locally. And yeah, we also do. We not only do like large language models, we also do image gen. So for example, here is what you can do with our open source repository, for example, for the Flux model, that is the second most liked model on Hugging Face. With our open source tools, you can kind of make it 4 times faster while still having a nice quality. You still have this nice, cute prune in the end. So feel free to check it out. And before I end the talk, I want to wrap it up a bit to kind of give you an overview of what we talked about today. So first, we talked a bit about tokenizers and how they are related to like efficiency, and that we maybe need like a Bavarian tokenizer as soon. Then we touched on distillation, which is a really nice technique that allows you to train these smaller versions of models and is used heavily right now, and also allows you to kind of produce like models that are really super efficient. Then we looked at KV caching, that kind of makes this attention operation that's really essential to transformers faster. Then I opened this metaphor of thinking about GPUs as a warehouse and tried to explain you how operation fusing, which is kind of used by flash attention, works. I also talked about quantization, that kind of shrinking like the models can actually be a good idea, and is surprisingly not like destroying the model performance. And in the end, we kind of saw how this team of a really smart model and a stupid model can kind of outperform the smart model alone. And yeah, that was it with my talk. And yeah, happy to be here. Thanks for the invitation. And if you have questions, I'm happy to answer.
Yeah, thanks a lot, Niels, for the super interesting presentation. I think, yeah, it was very well explained, very easy to follow. And thank you also for letting us know what you guys at Pruna AI are doing. Super cool stuff. Yeah, maybe while people still type in their questions, I have also a question. Like we saw different methods today to optimize these models, distillation, caching, quantization, as you presented now. Um, each of them has their trade-offs. And my question is, if we were to combine them, are these trade-offs cumulative, or how do they perhaps make the outputs twice as bad? Is it exponential? Do they sum up? Is there even any benchmark on this?
Yes, it's like a really, really interesting question in the end. So I think the good news here is that for many of the things I presented today, they don't really change performance, right? Something like KV cache or speculative decoding, they don't really change the output. Also, something like operation fusing is really nice in this way because it's just a different way of doing the computations. So these three don't change the performance in the end. And then I guess distillation and quantization, I guess if you do combine them, you get like worse outputs. I think they're not really orthogonal to each other.
Mhm.
But what's really interesting is I can tell you this for like image models. It's sometimes interesting because you have two different ways of making models faster, and they are really orthogonal to each other. So and it's sometimes they actually sometimes it's interesting because combining two approaches can lead to better results as you would have expected it. So but it's like something image gen specific, which probably takes a bit of a time to explain properly. Yeah, but
Yeah.
really interesting question.
Mhm. Thank you. Yeah, then let's go over the questions in the chat. Let's take them in order, maybe. Nika was asking a question: is distillation task specific?
I think you can make it, right? I mean, it's like super flexible and you have really much control in how you want to prompt like your large teacher model to produce some synthetic data, right? So if you want, you can, and I think that's also a cool application of it is to kind of use this huge target model that kind of knows about everything to then produce you some synthetic data about like one specific area on which you want to train a smaller model. I think that's a really cool application of distillation. Yeah.
Mhm. Thomas was asking, what quantization scheme do you find the most promising or interesting? Where is the open source community still missing some mixed precision, quantized kernel implementations or tooling?
Okay. Oh wow. Challenging question. Let's see. I think so. The thing I presented is like this yet another quantization algorithm. I think that's right now what we believe is really, really promising. Unfortunately, it's not really truly open source, but if you're like, I think you can use it, and I think it's really promising right now. Sometimes I think there's also a bit of a trade-off that I didn't really touch in this talk, but if you use a too complex quantization scheme that kind of preserves maybe the quality, it can be sometimes also slow because maybe something I did not really mention much is that sometimes these quantization algorithms they also come with some overhead because maybe you have to transform like the numbers back and forth to the quantized form and back to floating point numbers and so on, which can also like sometimes hurt your performance. So sometimes I actually prefer like simple quantization to really get like the best speed up. But I have to admit I'm not the expert on quantization for LLMs.
Mhm. Nika is also asking, how does batching help to speed up computations if anyway all tokens are computed by target model as well? Slide 35.
Yeah, I think okay.
I
Let's.
think you explained this already, right? Maybe
I think yeah.
afterwards.
The idea is I think it doesn't really make it faster, but the idea is kind of that the idea is you can basically generate just more things in parallel without it taking much longer because the dominating part here is like this moving the weights around, and then you can maybe move the weights around with like multiple inputs for different generations, and basically can do more generations at the same time. I think that's the idea, right? Yeah.
Mhm. Maybe related to my question, which one do you think works better, quantization or distillation?
Whoa, really hard one. I mean, that's not something I don't think about too often because distillation is like really, it can be really compute intensive. So that's not something we do at Pruna. Uh, I personally think I would prefer distillation, but of course, the downside is that it really takes a lot of compute. You have to train a new model, basically, right? And generates a lot of synthetic data, it needs a lot of knowledge. Whereas I think quantization is really not neat in a way that you can just like throw it onto some model. There are like really cool libraries, for example, like our library, where you can really easily like throw it at some model. So yeah, I think I would prefer like when I really care about performance, distillation, but in the end, as an end user, you maybe have no other choice but use quantization.
Great. Kaiwei is asking if you think early exit strategies are promising where the inference is stopped before the final layer.
Um, yes, I think it's something we also looked into. I think so far we did not implement it, but I think it looks promising, and I think it also like tackles this problem I described, right, with like having these super huge models, and sometimes it's really pretty straightforward what the next token will be, and I think then it makes sense to use these kind of strategies. But I also can't tell you if it like works better than, for example, speculative decoding, right? But it's I think interesting at least.
And the last question we have in speculative decoding, why can we save computation if we still call the larger model besides the draft?
Yes,
Yeah.
I think that's actually a really good question, and also to me it wasn't really intuitive at the beginning, and the reason there is kind of what I said, right? With this batching, like because we're so memory bound, like this batching works well. So for example, if you have like you can really like parallelize things well with our like that is really fast. And so what you do instead of like what if you just would use the target model, you would kind of generate token by token by token by token. But because of the draft model, you already have like this long text, so you can kind of parallelize this. It's a bit hard to explain, but I think that's the reason why it's faster because you can kind of batch it a bit.
Great. Actually, one last question from Philip, who had to leave, but he wanted to know if you have any recent research paper that you've read or any direction within the NLP topic that you find particularly interesting, not only related to this area, but yeah, in general.
Oh, hard question. I mean, for inference, I would really say like this quantization paper I discussed is something that we think about a lot. I think that's really promising, really interesting. Overall, I think there's a lot of cool stuff. I think like what I really liked was the things Anthropic did for interpretability of these models. I think that was really amazing and really easy to understand. I really like that. Yeah.
Yeah. Lots of things going on, that's for sure. It's hard to keep up with all the new advancements. Yeah, to close up, well, there's another question. Can we get the slides? This video will be uploaded to our YouTube channel. So yeah, you can go through it again. And of course, see the slides there as well. But yeah, to close up today's event, I want to remind everyone that we have more events coming up very soon. You definitely don't want to miss them. First of them is this token 7B and beyond, shaping the multilingual future of LLMs by Dr. Michael Fromm. This is a new model, like large language model developed by Open how's it called? Open GPTX, sorry, which is trained in European Union languages. And they use a custom tokenizer for that. That's already this Saturday at 3 p.m. And then the next one that we have scheduled for next week, also on Tuesday at 7, it's BMO, which is a benchmark that focuses on generation or detection of machine generated texts. And especially they focused on the multi-author scenario. So with that, and we conclude today's meeting. Thank you so much, Niels, for your great presentation and for your time. And also to everyone attending, thank you for being here. And yeah, we see us in the next event.
Thanks for having me. It was a pleasure.
Thank you very much.